Hi everyone, I'm Billy, the Science Leader at Open Force Field, and this is the OpenFF Science Update for March 2025. The format of these is that I'll present and summarize progress that we've been making over the past months on projects that align with the initiative roadmap goals. So, first up is quantum chemistry data generation and management. And this will be an ongoing item as QM calculations are one of our key sources of training and testing data. Jen, who has taken the lead on establishing dataset strategy, has been investigating a few different options for long-term storage of the datasets that we use in fitting and benchmarking force fields. So the goal here is to establish a generally usable record of our data that will last beyond, say, different versions of specific Python libraries, Python updates, and beyond even the Open Force Field and the MOSI-QC archive itself. So this is quite a lot to ask, and Jen spent some time comparing different options before settling on the SQLite view format that was recently implemented into the MOSI-QC stack. We will also be adding an accompanying Docker image with a working environment that can be used to read this file into Python. So the pros of the SQLite format are that even outside of Python, SQLite is a fairly common and generic database system that can be read using many other tools. It also takes up a lot less disk space than some other formats, such as JSON. And finally, just using the QC archive view format means that we don't need to define another complex additional schema. So the next steps here are to iron out any infrastructure needs and trial uploading one of our past fitting datasets. That being said, QC archive is in the process of updating some of their class structures and adding a new way of grouping datasets into what they call projects. So as this may affect any workflow and products that we develop here, this project is currently kind of waiting to see what happens there. Jen has also been developing some new infrastructure for handling and deploying remote compute workers called QB-Custom, which is enabling more efficient compute management. And finally, just as a point of interest, this isn't one of this year's big roadmap items, but instead an additional collaboration with Genentech. Jen has been working on improvements to our infrastructure to handle transition metal complexes. In terms of actual datasets and progress since last month, we have completed the lipid maps optimization set for possible future lipid fits. We've completed an additional optimization dataset of peptide tetramers for protein force field fitting, which was contributed by Arnika. And we've completed an additional set of molecules for troubleshooting issues with torsions that were identified by Crescit. In progress, we still have the lipid maps benchmark set, although that's very close to finishing, and an initial set of transition metal complexes from the PDB CCD. Moving on to more general force field work. Over the past couple of months, we've realized that our current workflow for fitting van der Waals terms to physical properties was, in some cases, computing those properties from simulations that hadn't equilibrated properly within the time span allowed, and in some cases, in any reasonable time span. So we investigated and found that some poorly equilibrating molecules were highly viscous and may need much more time to equilibrate from any perturbation than we could afford in terms of compute. We're now trying to fix this issue in two ways. Firstly, by filtering out compounds that we know are very slow to equilibrate. And secondly, by introducing a split workflow where simulation boxes are pre-equilibrated before being used in a fitting pipeline, which we hope will result in better sampling for less compute cost. So this is all currently in progress. After identifying and excluding other slow liquids, we plan to select a new training and validation set and refit Sage. Moving on to the biopolymer force field, this is another recurring topic. This project is driven by Chapin Kavada at the Gilson Lab, and the goal here is a Smirnov protein force field that approaches the same quality as existing protein force fields, such as AMPA14SB. To very quickly sum up 3 years of work, Chapin has found that simply refitting Sage to quantum chemistry data resulted in force fields where the secondary structure of GB3 unravels in long timescale simulations. So Chapin is now pursuing a direction where he refits backbone torsion parameters to NMR observables and had been making pretty good progress with regards to the said NMR observables, but hit a plateau. After ironing out some bugs, we think the primary cause is likely due to sampling issues in the training data, and the overlap between different windows from umbrella sampling over the fraction of native contacts could be quite low. So Chapin is looking at a number of ways to improve sampling. One easy approach was to loosen the energy constant of the biasing potential, which improved sampling substantially. That being said, running an additional fit to this better sampled data resulted in a performance regression, which suggests that this is not the final solution. So Chabon is also looking at using replica exchange, which might give better results. Our next two projects are newer ones. First up are Julianne's efforts towards a lipid force field. So like the protein force field project, the end goal here would be to have a force field that performs to similar quality as existing lipid force fields. The first question that Julianne looked at over the past couple months was how well our existing Smirnov line performed compared to established lipid force fields, and she found that there were some notable differences and defects. So looking at POPC bilayers in SAGE, she compared them, their performance to the same bilayer in Makarov and S-lipids last year, and she found that the lateral diffusion of the lipids was very slow in SAGE. In a more recent comparison of parsley and SAGE to CHARM36 and lipid 21, she found that the order parameter quality was lower for both Smirnov force fields shown here compared to the other ones, and that the correlation time was very high. We did note that SAGE was trained to very few simple alkanes and phosphate molecules, which might affect the valence parameters here. So this year, Julianne experimented with refitting SAGE to additional training data that covered both these chemistries. She ran two refits, one where all the additional data generated was adding to the training set, SAGE 2.2.1 core, and one where it was randomly sampled, so SAGE 2.2.1 orgs. With both refits, however, she found that the order parameter quality or correlation time of a POPC bilayer was not improved. At the FI meeting in February, it was suggested that it might be the non-bonded parameters of SAGE that were resulting in kind of overly sticky interactions. Preliminary investigation here, however, is showing that replacing the Leonard-Jones terms of the phosphate group oxygens with slightly larger terms from amber doesn't seem to improve the correlation time, but might improve the order parameters slightly. There's a couple of caveats here. Firstly, the simulations are still in progress. And secondly, lipid 21 doesn't actually use these larger oxygen terms, but does still achieve decent performance on the POPC bilayer. In terms of next steps, Julianne is planning to benchmark an additional force field fit, where she loosened torsion priors to allow the alkane and phosphate torsions to move more freely. She's also going to look further into non-bonded parameter experiments and additional torsion data. And last but not least, we're starting to experiment with bringing order type parameters into the force field creation workflow. So Trevor Goki has created the BSmarts library for automatically generating parameters based on training data. And Josh is working with Trevor to understand how best to bring this into a production pipeline. Our first test project is seeing if BSmarts can generate good candidate torsions for better torsion profile fits in the problem space identified by CRESID. And hopefully we'll have more to say about this next month. So thank you very much for listening. See you next time.